Our next talk is Steve Wanzell. He's going to be talking about forest harvest effects on temperature of small headwater streams with and without buffers. Steve is a research ecologist with the PNW Research Station in Corvallis, and I'm so glad we're talking about headwaters, class 4s, because I remember 20 years ago standing out and arguing with people about their value. Was it even something that we needed to think about? So yes, we do need to think about it, and Steve's going to talk about it. So help me welcome Steve. Come on, Steve.
Well, thank you very much, Cheryl, for inviting me to attend, and it's a pleasure to be here and to have a chance to talk about a project that we did when I was located in Olympia, Washington. This was a joint project that we did with Washington Department of Natural Resources and Washington Department of Ecology, and two of my co-authors, Jack Janisch and Bill Enger, are both employees of Department of Ecology. And I also had a lot of help on the project from colleagues in the PNW Research Station, Pete Bisson, and field help from Alex Foster, Shannon Clausen, and Jeff Rickliffs. The results the work I'm going to present to you today has been published. It was published in Forest Ecology and Management earlier this year. So if you want to get the full details, you're welcome to turn to that that paper. And I'm going to guess. Oh, good, that's the pointer. The motivation for this particular study was twofold. The motivation for the state of Washington to be involved in this study was as kind of a monitoring and evaluation of existing forest practices rules in the state of Washington. Small headwater streams in Washington that are harvested on private or state lands do not require any kind of riparian reserve along them, so clear cutting can go right to the stream banks. The Forest Service's interest was an opportunity to test various kinds of buffer designs and their impact on stream temperature responses following harvest, where we could actually have treated watersheds that were completely clear cut. So we had a total of 8 clusters of sites. 4 of these sites were located in the Capitol Forest on state lands just outside of Olympia, Washington, and another 4 were in the Willapa Hills closer to the ocean and also on state lands. This study would not have been possible on Forest Service lands because of the limitations on forest harvest. So I'm going to talk to you today about something that's quite a lot different than what Jeremy was talking about. I want to talk about small streams. And maybe it'd be better to say absolutely tiny streams. In fact, streams that are often so small that they go dry in the summer, and that turned out to be a problem for our study design. So these watersheds were 1 to 8 hectares in size, and minimum summer stream flows were down to less than 1 liter per second. So this is a 4-inch PVC pipe through one of the weirs at the bottom of one of the treated catchments. Okay, and that's the kind of stream flow that we're interested in. And are those streams being impacted by forest harvest? Clearly, it's not a fish-bearing stream. So what were the harvest treatments we wanted to study? So this is a layout that shows 2 of our harvest units. This is the tags and the rot units here. Again, non-fish-bearing streams. All of these tributaries flow into fish-bearing streams, Potosi Creek here and Camphor Creek here. And our little study watersheds are outlined here in white with our little non-fish-bearing streams. In all of the cases, because the larger streams are fish-bearing, the state forest practices rules require substantial no-cut buffers alongside those streams. So those buffers extend into the bottom ends of our treated watersheds. And then our treated watersheds had a variety of treatments. So here were the controls, which were non-harvested, although in places a little bit of harvest might slop over the watershed boundaries. We had streams that were set out to be continuously buffered with, on average, 10-meter wide buffers on each side of the stream, so about a 30-foot buffer on each side of the stream. as shown here or here. We had clear cuts here, here, and we also had a kind of buffer we called a patch buffer, where rather than a continuous buffer on the full length of the stream, we'd keep the same 10-meter wide buffer, but it would be discontinuous along the length of the stream. So it's shown here, here, or here. And you can see some funny things with the patch buffers. Like in this case, the buffer is located at the bottom of the watershed. Here it's up at the top of the perennial flows in the stream. In this case, the the actual wetted channel was really, really small, and the patch buffer buffered almost the full length of the channel. And then we also had some leaf trees that, this was an operational study. We wanted to do a test of forest harvest the way it's actually being practiced on state lands in Washington. And so the way these cutting units were designed, they simply would not have cut these because of what their interest in cutting were. So even in some of our clear cuts, there were substantial amounts of trees left behind. And then in some places, for other reasons, unstable slopes and things like that, other trees were left behind. So the clear cuts weren't necessarily entirely clear cut. And then we located our monitoring sites right at this boundary with this main stem buffer and put a thermograph in each of those locations. And because we had two agencies doing monitoring, Forest Service and Department of Ecology, the Forest Service, my work, we used I-button thermographs, very small, with a resolution about 0.5 degree C, and Department of Ecology used tidbit T thermographs that have a resolution about 0.2 degrees C. So there's a little bit of difference between the studies and who were doing the monitoring in any individual watershed. So these were the two questions we were interested in asking from our study. Does forest harvest increase stream temperature? Again, in these tiny, tiny, tiny headwater streams. And if forest harvest does increase temperature, would our buffer designs somehow limit those temperature increases? Well, it turns out that this is not an easy question to answer, and there's a lot of statistical work needed to do before you can extract the signal out of the data. So here's an example of one of our watershed pairs, where I have in green is a control watershed, and red is the treatment watershed, but this is in the calibration year before any harvest had occurred. We are only interested in summertime maximum temperatures, and we only look at temperatures between the 1st of July and the end of August. We have 60 days across here, and the temperatures here are plotted on the y-axis. And as you can see, the treated stream was warmer than the control stream before any logging was done. So if we were to go in and log the treated stream and come back and measure the temperature and say, well, it's warmer, well, would that be because of the harvest, or would that be because of some innate difference between the watersheds? So we needed to try and correct for these kinds of differences between watersheds. So the way we did that is we used this calibration year, here's the graph I just showed you, and plotted the temperatures we observed in the control watershed in green, which are here on the x-axis, and used a regression equation to relate them to the temperatures observed in that calibration year on the treated watershed. It's kind of a messy regression equation. We had a really good fit. So it doesn't look like your normal simple linear regression. These two terms, this sine term and this cosine term here, allow there to be differences with changes in seasons. Okay? If you look at the kinds of temperature responses that people observe in the literature, you'll see that very often the summertime temperatures are warmer, but in the wintertime, when the sun's low on the horizon, it turns out logging doesn't have much of an effect. So these terms here allow us to correct for those seasonal differences and make a complex equation. And then there's this little e over here, the error that's always with us when we do a study. And when we do a time series study, we end up with these regression equations, some autocorrelation in the residuals of the regression. And so we have to model that and try and remove that from our analysis. And I'm not going to describe that. I don't have time today to describe that, but I just want you to know that I did that. okay? But just, you can, but what we do then is we take this regression relationship that we develop in our calibration year, and we go into the first treatment year, so this is 2005, when our watershed had been cut. We observe temperatures in our control watershed. Again, this is 2005 observed temperatures each day of the summer. And we use those observed temperatures with this regression equation to predict what the temperature should be if the treated watershed had not been harvested. And that prediction is in this black line here at the bottom. And then we go into that treated watershed and we actually put our thermograph in there and measure the temperatures. And the red dots are what we actually observe, okay? So that we've corrected now for this background difference between these two watersheds. And this signal between observed and predicted temperatures is the treatment effect for that watershed pair. It's kind of messy. We have a whole bunch of watersheds, and if I just walk you through a whole bunch of dot plots, your eyes will glaze over. So what I've done is we focus on the difference here. So instead of expressing this as an actual temperature, we express it as a temperature difference by subtracting the predicted temperature from the observed temperature. And then I just take those and express them as a box and whisker diagram where there's a temperature difference on the y-axis. Here's 0. If all the points plotted at 0, there'd be no temperature effect from logging. The mean is the little line in the middle. The top and bottom of the box is the 25th and 75th percentile of observations. The whiskers are the 10th and 90th percentiles, and the dots are bigger than that. So we have a whole bunch of data, and they're all going to be shown here as box and whisker plots. So go back to what we were trying to do. These are the treatments we wanted to look at. Does the forest harvest have an impact, and do the buffers change that impact? Well, we have 8 sites, and at each site we had a cluster of watersheds. So we should have had a nice, beautifully balanced design for statisticians to get excited about. All the red boxes are reasons that statisticians wouldn't be excited. We should at each of these sites have a control, a continuous buffer, a patch buffer, and a clear cut. And right away you can see that there's no patch buffer there. Down here, we had no patch buffer, but we made up for it by having 2 clear cuts. You know, it's an operational study. The world can be messy, and we wanted to know what was the impact in a real-world situation, not in an elegantly controlled scientific experiment that may have limited application to the real world. The other problem we had is some of our watersheds went dry. It's particularly frustrating when you do a whole lot of work and your control watershed goes dry. You know, some summers are drier than other summers. We laid out the study before we had taken lots of measurements on the stream. We didn't expect that these streams would go dry. That's just the real world. So that we had a number of watersheds that we couldn't analyze. But the ones that we were able to analyze told us a really nice story. So here are all the box and whisker diagrams, all right? What I've shown here in this large area in gray are all the comparisons between our reference pairs of watersheds. The green ones show the continuous buffered watersheds, the yellows are patch buffers, and the clear cuts are here in red. We have the temperature effect on the y-axis ranging from 0 in the middle, which would be no forest harvest impact at all, going to -2 to +4 degrees. Each of the specific treated watershed, control watershed pairs are shown by a box and whisker diagram. And the mean response for this block of treatment watersheds is shown in the bold dashed line here. So the first thing you can see is that our reference pairs of catchments are completely different than our treated watersheds here. So when you have a treatment reference comparison, you always know that you're supposed to use the control to predict the temperature in the treated watershed. But if you compare control A to control B, which one do you use to predict the temperature in the other one? You can use A to predict temperatures in B, but it may make just as much sense to use B to predict temperatures in A. And just by chance, our reference pair comparisons are going to be slightly different. So that's what's happening here. You can tell that these are kind of arranged in pairs. This is A used to predict B, and then B used to predict A. And in one case, it's slightly warmer. In the other case, it's slightly colder. And it should be no surprise that the mean response here would be exactly 0 because we're taking mirror images around this variation. But what is important is to look at the variation amongst these responses when you do reference-to-reference comparison. And that's what this gray line here is basically 2 times the standard deviation of this variability here. And it gives you a measure to look over on this side of the diagram and say, what would we expect to be a really significant difference that this technique could measure? So for these boxes that are falling inside the gray zone, we're essentially seeing no response of forest harvest whatsoever. But other ones, like this one, show really dramatic forest harvest effects. But we were kind of bummed in some senses. We expected that clear cut should show the biggest response, that continuous buffer should show the least response, and that patch buffer should be somewhere in between. So yes, we did see the biggest response in clear cuts, and the average effect here was 1.5 degrees C increase in the first year after logging. And yes, continuous buffers were smaller, but our patch buffers were smallest of all. The other thing we saw was we didn't have consistent response. Here's a clear-cut watershed that basically didn't change. And we see that's true for patch cut and for continuously buffered watersheds as well. So we got really messy results. Yes, you could conclude that forest harvest does have an impact. There's a bit of an indication here that buffers were important, but in all of our treatments, we saw some watersheds that responded and some that didn't. So some watersheds appear to be temperature sensitive. Again, these tiny, tiny headwater streams, temperature sensitive to forest harvest and others aren't. Well, fortunately, Jack Janisch, colleague from Department of Ecology, looked at his subset of watersheds and measured these descriptive variables here, measured elevation, et cetera. We'll have reasons to think that these things might somehow be related to temperature and temperature response. High elevation watersheds ought to be colder, perhaps, than low elevation watersheds. These were all in the coast range and it isn't very high, so elevation doesn't vary tremendously. But we did have watersheds that varied in size from 1 hectare to 8 hectares in size, so we have bigger streams. Maybe they wouldn't be as responsive. We had some that were north, south, east, or west. That could be an important factor. And so he measured all of these things. Now, I do want to take the time to say we did not have a direct measure of shade. We instead have something that we decided to call canopy and topographic density. We had hemispherical photographs that were taken at a couple of points in each watershed, but when we calculated what portion of the sky was obscured, we did it for a full 360-degree view over a total 180 degrees of the canopy. So, you know, the trees on the north side of the stream just don't have any effect of casting shade. So we don't have really good shade. Well, we did a correlation analysis to ask the question, which of these is significantly related to the temperature responses we saw? And we came up with 4 that were significantly related. We have one I have a question by. It turned out that north-facing streams were warmer than south-facing streams, which doesn't make any sense mechanistically. But I'll come to an explanation. And then we saw that these 3 terms here were in fact significantly related to temperature response. So we'll look at those a little bit more. So we have length of wetted stream channel here and wetland area here increasing on the x-axis. We have our temperature response on the y-axis. The symbols show the treatment, continuous patch, and clear cut. The solid ones were in fine textured stream beds. The coarse ones, the open ones were coarse textured stream beds. And so what you can see is if you have coarse textured stream beds, the temperatures didn't change. And the more length of wetted channel or the more watershed area in a wetland area in these tiny watersheds, the bigger the temperature response. So the way we interpret this is that the more surface area in these headwater watersheds that was exposed to the ambient environment, sunshine and wind and et cetera, the bigger temperature response we saw after harvest. But if the stream bed was coarse, there was probably a lot of hyporheic exchange that prevented those increases from occurring. Okay? And it doesn't seem to make a difference what the treatment was. These lines work really well when you ignore whether it was a continuous patch or clear-cut treatment. Okay? So this seems to be, these factors are controlling how sensitive the watersheds are to temperature responses after the forest harvest, and that whether it's a continuous buffer, a patch buffer, or a clear-cut made little difference. So, yes, some of our treated watersheds got warmer, but on average, those increases were quite small, 1.5 degrees at the most on average for clear cuts. The trend did not meet our expectations, and the responses were really highly variable within treatments. But we did see that those responses were highly correlated to the amount of surface area that was exposed to sunshine and the amount of hyporheic exchange. And it turned out that all of the north aspect watersheds, oh boy, I'm going to get this backwards, had attributes that would make them non-sensitive to temperature. And also, all the patch-cut watersheds were on gravel-bedded streams where there's a lot of hyporheic exchange, so they were not responsive. And finally, I want to remind you that we looked at tiny streams. And there's reasons to think that larger streams would respond differently, so I don't think that these results are applicable to large fish-bearing streams. Thanks.